Today we're going to be talking about Section 3.3, Day 2, which are more complex rules for differentiation. So far we've just been working primarily with the power rule and some basic sum and differences. And today we're going to get into some meatier rules having to do with the derivative of a product and the derivative of a quotient. So first we'll just write the rules down and then we'll go through some practice about what it actually looks like to put these into practice. So the first one, the derivative of a product. Okay, so if I have two different differentiable functions, f of x and g of x, then if I were to take the derivative of their products, so f of x times g of x, and I want the derivative of that product, here's what it looks like. I take my first function in the product, which is f of x, and that stays as is. And then I multiply that by the derivative of my second function, which we're calling g of x. And then I add my original function, g of x, times the derivative of f of x. So that is my product rule. The next rule we have is the derivative of a quotient. And so now again, our setup is we have two differentiable functions, f of x and g of x, and now we want to find the derivative of their quotient. And so here, what we're going to do is we're going to take our function in our denominator, which is g of x, and then we're going to multiply that by the derivative of our numerator, so f prime of x, minus the function in my numerator times the function, or the derivative of the function in the denominator, all over the function in my denominator squared. And the phrase you'll hear me say a lot is low d high minus high d low over low squared. And so what I mean is if I call my f of x my high function, because it's in the numerator, and g of x is the low function, because it's in the denominator, then I take low, d high, or the derivative of my numerator, minus high, d low, all over low squared. So let's actually look at some examples to get some practice with that, and then I think it'll make some more sense. So for number one, we're going to find the derivative of this product. So I have one function, x squared plus 1, and then my second function is x cubed plus 3. So we're going to use our product rule. And that rule told us to take our original function, the first one, we're going to just keep that the same. It's going to stay x squared plus 1. Then we're going to multiply it by the derivative of the section function. And that derivative of x cubed plus 3 is just going to be 3x squared. And now we do the reverse. We're going to add x cubed plus 3 times the derivative of our first function, which is just 2x. So now we've got all the pieces. We just need to distribute, combine our like terms, and simplify this a bit. So I'm going to distribute this 3x squared to both terms. So I'm going to get 3x to the fourth plus 3x squared. And I'm going to distribute 2x to both of these terms and get 2x to the fourth plus 6x. And so the last thing I'm going to do is combine my like terms. I have a 3x to the fourth and 2x to the fourth. So I have 5x to the fourth plus 3x squared plus 6x. And that's our derivative f prime of x. So that's an example of the product rule. Okay, my next example is clearly a quotient, so we're going to practice with that quotient rule here. Again, I have my top function in my denominator, and then another function or in my numerator, and then in my denominator. So if I look at the derivative, we said we're going to start off with our low function, which is x squared plus 1. So we said low d high, which means the derivative of our numerator, which is 2x, minus high, which is x squared minus 1, d low, which is the derivative of our denominator, all over low squared, so x squared plus 1 quantity squared. So now we're going to do some basic simplification, again, especially in the numerator here, by distributing this to both terms. So 2x cubed plus 2x minus 2x cubed. This would be a negative 2x, so that's going to be plus 2x all over x squared plus 1 quantity squared. And so now we notice our 2x cubes cancel, and I'm left with 2x plus 2x, or 4x over x squared plus 1 quantity squared. And that's our derivative. Okay, so now we're just going to do two more quick examples again so we can kind of get used to how these rules work. So we're going to go back, and this one is going back to our product rule. So my first function is 1 plus t, and we're taking the product of that and my second function, which is square root of t. So we're finding s prime. So again, I take my original function, which is 1 plus t. And actually jumping back here, it may help to think of this as 1 plus t times t to the 1/2. So we see that's just an application of our power rule. So I take my first function, 1 plus t. I'm going to multiply that by the derivative of my second function, which is 1/2 t to the negative 1/2. And then I'm going to take my second function, which is t to the 1/2, times the derivative of my first, and this one's kind of nice because the derivative of 1 plus t just comes out to 1. So now, I'm going to go ahead and distribute this 1/2 t to the negative 1/2 to both terms. So 1/2 t to the negative 1/2 times 1 is just 1/2 t to the negative 1/2 plus, now when I distribute this, I have my 1/2. We know when we multiply powers, we have to add those exponents. So 1 plus a negative 1/2 just gives me t to the 1/2 power. And then I have my last term plus t to the 1/2. So if I combine my like terms, I have 1 over 1/2, t to the negative 1/2 plus 3/2 t to the 1/2. And we could leave our derivative right there. However, I'm going to rewrite this. I'm going to get rid of those rational exponents and write them as square roots. So this is the same as, I know t to the negative 1/2. That's the same as moving it down in the denominator with the square root. So I have 1 over 2 root t plus 3 over 2 times the square root of t. So those are both expressions that represent the same derivative. Okay, to wrap up, I'm going to do, on this side anyway, do one more quotient rule. Again, that low d high minus high d low over low squared. So here we go. Our low is x plus 5. The derivative of my numerator, my high, is 3x squared plus 4x. Then we're going to subtract our function on top, x cubed plus 2x squared minus 1, times the derivative of our numerator. That's our d low, which is just 1. And that's all over x plus 5 squared. And so that's really where all the work of the rule is done. The rest is just simplifying this into something a little cleaner. So I'm going to FOIL here. So I'm going to get 3x cubed plus 15x squared plus 4x squared plus 20x. And then I'm going to subtract these terms here. So minus x cubed, I'm going to distribute that negative, minus 2x squared, and plus 1, all over the quantity x plus 5 squared. And so if I have any like terms, here I have 3x cubed minus x cubed, so 2x cubed. 15x squared plus 4 gives me 19 minus 2 is plus a 17x squared. And plus 20x and plus 1 all over x plus 5 quantity squared is our derivative. So that's how those two rules function, and we'll get a lot more practice working with these tomorrow in class, but we want to talk a few more things before we leave this concept. So if I look on the next page, there are some tricks for sometimes being able to get around these rules. Okay, so sometimes what we really have is just a power rule kind of in disguise. Okay, so sometimes it might seem like we need to use the quotient rule, and in fact this also sometimes happens with a product rule. It might seem like we need those rules to differentiate a function, but really it's much easier to differentiate the function if we first simplify the function using some algebra. So if I looked at this function, it absolutely looks like a quotient. But I know that I can simplify this a bit. I can rewrite this as x squared over 2x plus 3 over 2x, which at first may not seem a whole lot simpler, but I can simplify this to x over 2. So now I have x over 2 plus 3 halves times x to the negative 1. That x in the denominator just becomes x to the negative 1. So now if I want to differentiate it, it's a simple matter of using the power rule. So x over 2 is the same as 1/2 times x. I know that derivative is just 1/2. And for my second term, I just use the power rule. I'm going to multiply my exponent times the coefficient. So I get minus 3/2 times x. And if I have a negative 1 and I subtract 1, that becomes negative 2. So again, my answer is perfectly fine that way. If I wanted to rewrite it without negative exponents, I would have 1/2 minus 3 over 2x squared. And I want to quickly show you how this can also apply to power rule problems. So, or product rule, excuse me. So if we flip back, I want to go back to number 3. And so product rule will absolutely get us to our answer, but it's also a little simpler perhaps, and maybe I'll do this in a different color so we can keep it straight. What I'm going to do this time is I'm going to simplify my function a bit first. So I'm going to take that same function, 1 plus t times the square root of t, but this time before I differentiate, I'm going to go ahead and distribute that square root of t. So now I get square root of t plus t root t, which is the same thing as t to the 1/2 plus t to the 3/2. Now to differentiate that, I have a simple power rule problem. And my derivative is just 1/2 t to the negative 1/2 plus 3/2 t to the 1/2. And you can see actually in kind of a lot shorter order I got to the same answer that we had above. So it's just a little bit of knowing of when you can apply some algebra to simplify it first, and when you actually need to use the product or the quotient rules. So that's the bulk of the material for today. The last thing I want to talk about quickly, back on the next page, is higher order derivatives. Okay. So here's what we mean by higher order derivatives. So the derivative f prime of x or dy dx is called the first derivative of y with respect to x. Okay, sometimes we want to look at the second derivative, or in other words, we take the derivative of the derivative. Okay, we denote the second derivative f double prime of x or d squared y dx squared. Okay, and as long as we have a function, we can continue to take more derivatives, and we call those higher order derivatives. And we can write prime or use those superscripts to denote which derivative we're finding. So essentially, these are not very tricky problems generally, but we're just finding derivatives of derivatives. So for example, in number 5, we're given a function f of x, and we want to find the first 5 derivatives. So our first derivative, these are basic power rule derivatives. So we're just going to do 12x cubed minus 6x squared plus 2x minus 4. And there's our first derivative. And we're just going to keep going. Our second derivative is just the derivative of the first derivative, so 36x squared minus 36x plus 2. Again, the derivative of that constant term just becomes 0. F triple prime of x, our third derivative, is now 72x minus 36. Now, instead of using those tick marks for that prime notation, I'm just going to use superscripts here to indicate that fourth derivative. And here we have, from this linear term, my derivative is just a constant, 72, which means from our last derivative, derivative of a constant is just 0. So that's what we mean by taking higher order derivatives. We're just taking derivatives of derivatives. Okay, so our next one, obviously just the same. This time we want the first 4 derivatives. So my first derivative is 3x squared minus 10x. Second derivative becomes 6x minus 10. My third derivative becomes 6. And then my fourth derivative is just 0. Oh my goodness, and you didn't see any of that. Here is what that looks like. But again, since it's basic power rule, that should not give us any trouble. So tomorrow we'll be working a lot with those product rules and quotient rules and making sure we have the hang of how to use those. See you tomorrow.